Welcome to The Explainer. Today, we're tackling a huge question. How does a machine actually learn? We're going to dive deep and break down the core engine that powers pretty much all of modern AI, step by step.
Okay, so let's just jump right in. This is one of the biggest questions in technology, right? And the answer, maybe surprisingly, isn't about writing a million lines of code with rules for every single possibility. No, it's about building systems that can figure it out for themselves, just by looking at data.
And that brings us to the core idea of deep learning. See, it doesn't just learn one complicated thing all at once. Instead, it learns in layers. It starts by noticing really simple things, like an edge in a picture or a specific sound. And then it uses those simple ideas as building blocks to understand more complex concepts, like recognizing a face or understanding a sentence. It's a lot like how we learn.
So if you're going to build a thinking machine, where do you even start? Well, you start small. The very first goal was to create a basic thinking unit, a simple computational version of a single brain cell, a neuron, the fundamental building block of intelligence. The first shot at this, the McCulloch-Pitts neuron, was basically just an on-off switch, kind of rigid. But then came the perceptron, and this was a total game changer. It introduced the idea of weights. For the very first time, the model could decide that some inputs were more important than others. And crucially, that importance could change. That was the key, adaptability. And believe it or not, this super simple model could already learn. For example, by tweaking its weights, a single perceptron can figure out the logical OR function. It learns the rule to activate if either of its inputs is on. I mean, it's a small first step, but it's a real step towards machine intelligence.
But it wasn't long before this simple model slammed right into a wall. A problem so famous that it actually slowed down AI research for years. It was a puzzle that showed the deep, fundamental limits of what a single neuron could do on its own. The problem was a simple little logic puzzle called XOR, which stands for exclusive OR. All XOR means is the output is true only if the inputs are different. So 1 and 0, that's true, but 1 and 1, that's false. Sounds simple, right? Well, for the perceptron, it was completely impossible. And here's why. At its heart, a single perceptron can only do one thing, draw a single straight line to divide two groups of things. But if you plot out the points for the XOR problem, you can see right away there's no way to draw one straight line to separate the trues from the falses. The math just doesn't work. You can't do it. The solution, when it finally came, was just so elegant. The big idea was, what if we don't use just one neuron? What if we connect them together in layers? By putting a hidden layer of neurons in the middle, the network could suddenly learn much more complex, curvy boundaries. It could finally crack the XOR problem. And you know, this wasn't just some clever hack. It was actually proven with a mathematical theorem that a network with just one hidden layer is powerful enough to represent any logical function you can think of. The problem wasn't the neuron. The problem was that it was lonely. By working together, they become incredibly powerful. Okay, fantastic. So we have this amazing, powerful network structure. But this just creates a whole new, massive problem. A modern network can have millions or even billions of these weights. How in the world do you find the exact right setting for every single one of them? The breakthrough was to reframe the entire problem. Instead of trying to find the perfect answer directly, we create something called a loss function. You can just think of it as an error score. It's just a number that tells us exactly how wrong the network currently is. A high score means you're way off, a low score means you're getting warmer. And the whole goal of learning becomes incredibly simple. Get that error score as close to 0 as you possibly can. Now, you could try to find the right weights by just guessing. And you can see here for just one neuron, you might get somewhere. You try some values, the error goes down, awesome. You try some other ones, it goes up, whoops. But imagine doing that for millions of weights. It's not just slow, it's completely, hopelessly impossible. So instead of blind guessing, let's visualize this whole problem. Imagine a giant rolling landscape that stretches out in millions of dimensions. Every single point in this landscape represents one possible combination of all the weights in our network. And the height of the landscape at that point, that's the error, the loss for that specific setting. When we first create our network, we start it with random weights. That's like placing a ball at some random high-up point on this giant error surface. And now the entire complicated process of learning becomes a really simple analogy. We just need to get that ball to roll downhill to find the lowest possible point in the whole valley. That lowest point is our answer, the point of minimum error. So, how do we find the fastest way down, especially when this valley has millions of dimensions and we can't see the whole map? All we know is where we are right now. Well, the answer comes from a really beautiful and, believe it or not, intuitive piece of mathematics. The algorithm is called gradient descent. And here's the core idea. From any point on that surface, we can use a bit of calculus to find something called the gradient. The gradient is just an arrow that points in the direction of the steepest uphill slope. So if we want to go down, we just take a small step in the exact opposite direction of that arrow. Simple as that. Okay, let's peek at the math for a second, because this is where the real magic is. Calculus gives us this incredible tool that lets us predict how our error will change if we move just a tiny bit in any direction. Basically, our new error is going to be our old error plus some amount that depends on the direction we step and, critically, on that gradient arrow. So to make sure our ball is always rolling downhill, we just need to make sure that second part of the equation is a negative number. The whole challenge boils down to this. What's the best possible direction to step in to make our error go down the most? And here is the beautiful aha moment. The math shows, without a doubt, that the fastest way to make that term negative, to decrease our error, is to move in the direction that is exactly opposite to the gradient. It just makes sense, right? If the gradient points up the steepest part of the hill, the exact opposite direction must be the steepest path down. And that's it. That's the secret sauce. The gradient tells you the fastest way up. So to learn to minimize our error, we just do the opposite. We calculate that gradient and we give every single one of our millions of weights a tiny little nudge in the direction that's perfectly opposite to it. And this is where the last piece of the puzzle falls into place. The amazing algorithm that actually does this calculation, that efficiently figures out the gradient for every single weight in a huge network, is called backpropagation. It starts from the final error and works its way backward through the network, layer by layer, figuring out how much to blame each weight and which way it needs to be nudged. All right, let's zoom out and put this all together. We've gone from a single, simple idea of a neuron all the way up to the mathematical engine that's driving modern AI. So let's just recap the journey. We start with simple little neurons that just weigh their inputs. We connect them together into these powerful networks. We define learning not as being right, but as minimizing an error score. We picture this whole process as a ball rolling down a massive hill. And we use the power of calculus, gradient descent, and backpropagation to always know which way is down, taking one small, smart step at a time, over and over again. This one fundamental process, measure your error, find the gradient, and take a step, is the engine behind almost everything we call AI today, from translating languages to spotting diseases in medical scans. And that leaves us with one final kind of mind-blowing thought. If this simple, iterative process of just rolling down a hill is all it takes for a machine to learn, what are the real limits to what can be learned?